You ever seen an application where all the dashboards are green, everything looks perfectly healthy, but for your users, it's completely broken? Well, today we're going to solve a fascinating technical mystery about these invisible pauses that can bring even the most critical systems to their knees. 1.5 seconds. That's how long a critical high-speed payment service would just disappear. Not crash, not throw an error, it would just vanish from the network. Poof. No trace. I mean, how is that even possible? It's like a ghost in the machine story, but for engineers. And we're about to find the ghost. Okay, let's dive into this. So, our story kicks off with a supercritical payment gateway. You know, the service that sits right in the middle of a customer's checkout and the bank. And this thing has a really strict rule. Every single request has to be handled in under 200 milliseconds. No exceptions. For months, everything was humming along just fine. Then, all of a sudden, the alerts start screaming. The P99 latency, that's your slowest requests, spiked from a respectable 50 milliseconds to a disastrous 1.5 seconds. As one engineer said, it was just vanishing. For that 1.5 seconds, it was like the service stopped existing. And of course, upstream services started timing out, checkouts were failing, it was a full-blown production nightmare. So the engineering team scrambles, right? They pull up all the usual dashboards. But what did they see? Absolutely nothing. CPU? Stable at 40%. Memory? Yeah, it was high, but it wasn't growing. The error logs were completely empty. And the database and all the external APIs were responding in a flash. By every single metric they had, the system was perfectly healthy. And that's the heart of the mystery, isn't it? If it's not the CPU, not the database, not the network, what in the world could be the culprit? What could possibly make a server just freeze solid while leaving zero evidence behind? Well, the answer lies deep inside the application's runtime itself. It's a place where, for a brief moment, the world literally stops turning. The bad guy in our story? A stop-the-world garbage collection pause. See, the application was keeping this huge 4 GB cache of transaction data right there in its own memory. And every so often, the runtime had to stop everything just to clean that memory up. So what exactly is a stop-the-world pause? It's a total, complete halt of your program. The runtime, in this case it was the V8 engine in Node.js, freezes every single thing. Your code, incoming requests, timers, all of it, so it can do a massive memory cleanup. This isn't a slowdown, you gotta get that. It's a complete temporary freeze. And this explains why all the monitoring dashboards were completely blind. The event loop, the very heart of Node.js, was frozen solid. That means timers couldn't fire, network callbacks couldn't run, and here's the kicker. The metrics reporting agent also stopped. It's like asking someone who's asleep to report on whether they're awake. It's impossible. The agent would just wake up after that 1.5 second freeze and go, yep, everything looks great. To really get our heads around this, we need a picture. So let's introduce a concept that makes this invisible problem really tangible. We'll call it the red block. Okay, so in a healthy Node.js app, the timeline is a busy place, right? Your code is running, it's getting interrupted by I/O events, network responses, little tasks are firing off. The event loop is just spinning away. Things are moving. This is what normal looks like. But now, look what happens during the pause. A giant red block just slams down on that timeline. It pushes everything else out of the way. And for the entire duration of that block, in this case a whole 1.5 seconds, the application's world just ends. Nothing else happens at all. So let's be super clear about what's on and what's off here. Your JavaScript, the event loop, I/O, timers, all frozen. The only thing running is the garbage collector itself. And why? Well, because the V8 engine needs total exclusive control of the memory. Think about it. If your code was changing things while the garbage collector was trying to move them around, you'd get chaos, memory corruption. So it has to stop everything to do its job safely. Now, you might be sitting there thinking, why on earth would a system be designed this way? It sounds awful. And you're not wrong. But it leads us to this really dangerous and often misunderstood trade-off in how we design systems. It's the classic battle between throughput and latency. See, systems built for high throughput, like a big data processing job, they often use tons of memory. They let garbage pile up, and then they take one big, long pause to clean it all up at once. But for a low latency system like our payment API, that's a complete disaster. You care about the worst case scenario, and one single massive pause just destroys your service level agreement. And this is where it gets really weird. It's a total paradox. You would think giving a process more memory is always better, right? Nope. In this case, it can make these latency spikes dramatically worse. A small amount of memory forces frequent but tiny little cleanups. But a huge chunk of memory? It lets the process save up all its cleanup work and then pay that debt all at once in a single, catastrophic pause. So, how do you fight a problem you can't even see on your dashboards? How do you tame this red block? Well, let's talk solutions, because this is how you build a truly resilient system. The pros, they design for what's called pause sensitivity. And the strategy really has three parts. First, you reduce allocation pressure. Simple enough. Just create less garbage in the first place. Second, you keep your memory heaps small. Run more instances with less memory each instead of a few giant ones. And third, you move those big caches to an out-of-band heap, like Redis, so the V8 engine doesn't even have to worry about managing that memory. And for our payment gateway, the fix worked like a charm. The team scaled out to more servers, each with a smaller memory limit, and they moved that big 4 gig cache out to Redis. And the result? Those major garbage collection pauses dropped from 1.5 seconds down to under 20 milliseconds, which was completely invisible inside their 200 millisecond SLA. Problem solved. Now, this isn't just some weird niche Node.js problem. Understanding this concept is absolutely critical for building any reliable high-performance service, because we have to learn to look beyond just the average latency. The really crucial thing to get here is that these pauses have a massive ripple effect. They create this hidden volatility in your system that can lead to cascading failures. Where the paused service A causes service B to time out, which causes service C to fail. It can even make your load balancers trigger false alarms and kill a perfectly healthy process just because it missed a single heartbeat check while it was frozen. So the big takeaway here is you have to monitor what actually matters for applications that are sensitive to latency. Stop relying only on average latency in CPU. You need to specifically measure the maximum garbage collection pause duration. Tools like perf hooks in Node.js can plug directly into the V8 engine and tell you exactly how long the world was stopped. And that leaves us with one final, provocative question to think about for your own systems. Take a hard look at your dashboards and ask yourself, are they showing you reality? Or are they just showing you what happens when the world isn't stopped?